Okay. Like I said a little bit ago, we've got one last kind of shape to talk about, and that is the parabola. So we've done the ellipse, we've done the hyperbola. The one last conic section that we would have gone over on that very first day of this unit, where I showed you kind of all those different ways to like slice the double cone, is the parabola. Okay. Now we've talked about parabolas before when we were dealing with like quadratics. We know kind of what a quadratic looks like. We know what those parabolas look like. These I would say are similar to that, okay, but they are a little different in that they're not going to be like, we're not going to be factoring, we're not going to be um, using a lot of the things that we would have done with a quadratic, like finding our vertex and stuff like that. There's other ways that parabolas can represent these types of graphs. So they look like the parabolas that you've seen in the past, but we're going to handle them a little bit differently. Like we've done with all the other sections, we're going to go over how you graph a parabola when it is centered at the origin, and then how you graph a parabola when it isn't centered at the origin, and then also how do you write the equation of the graph. I would say out of all the things that we've done in this chapter, parabolas have the least amount of things that you have to find in order to graph it. So they are different than like the ellipse and the hyperbola. Those were really similar in that you had to read a lot about the graph, understand what order it was written in, what the x and the y squared are telling you, how to find all those pieces, the vertices, the foci, all that stuff. We don't really have as much of that to do with our parabolas today. Okay, so a parabola, just kind of this general definition here, is just a set of all points in a plane, okay, that are equidistant from a fixed line. There's something going to be called the directrix on here, and then there's a fixed point called the focus that is not on the line. So it's not on that directrix line, it's not on the parabola. So you can kind of see a picture of what this looks like. My parabola still has that U shape like we're used to seeing, but we'll have this point, the directrix, and we'll also have the focus. Those are going to be 2 points that we try to find in order to help us graph them. And it just kind of gives us an idea of some like parameters, again, kind of like those asymptotes, just some pieces that this parabola has to have in order for us to graph it. And then depending on what type of parabola you have, the axis, either the x-axis or the y-axis, will act as a symmetry line. So it'll cut your parabola in half and it'll look the same on both sides. If they were just put at the origin, they're going to look like these two ideas down here. So these are your standard forms. These would be like the parent graphs before we do anything changing the center or anything like that, trying to move it and manipulate it around. The one on the left, the standard form, is when it's y equals 4px. So when the y comes first, so before the equal sign, then your parabola is going to open either like to the right here. It could possibly open to the left. We'll talk about what needs to happen in order for that to occur. If the x comes first instead, though, so if it's x squared before the equal sign, that's going to change the direction of your opening. So instead of opening to the left now, or to the right, it's now opening up. Okay, and again, it could open down. It just depends on how the graph is written. In here, we'll find our vertex. For the first ones, the vertex will just be 0, 0, because they're going to be put at the center, and then eventually we'll move them away from the center. We'll have our focus point, and we'll have our directrix that we find. The focus and the directrix are actually related to each other a little bit, so if you find one, you're easily able to find the other one. So we'll go over how to do that. Something to just kind of maybe highlight or keep in mind is what they're writing here. For that first one, when the y comes first, the directrix is always going to be x equaling your negative p, and that comes from that equation up above. And then on the right side, it looks the same, but we are switching it to y equals the negative p. And then when you have the y equals type of a parabola happening, your x-axis is going to be the line of symmetry. And when the x squared comes first, the y-axis is going to be our line of symmetry. So just keep that in mind. Some of those things are going to always tie together when we're graphing these parabolas. So if we turn the page, I'm going to show you our first example. And again, this is going to kind of have some stuff worked out for us, and we're going to talk about how they got there. and then we'll start doing some by ourselves. Okay, in order to graph a parabola, if it's centered at 0, 0, the only things that we need to find are our focus and our directrix, and then we can use those things to help us graph the parabola. So they're going to give you something that looks like this. This one is starting out with y squared equals 8x. I also am just going to write underneath this from our form on the other side. This came from y squared equals 4px. There's always a 4, and then the p and x just follows it. That means if I wanted to solve for my p, the x's are kind of already both in the equation there. So the 4p part of it, so this piece here, connects to this 8, and that they have to be equal to each other. So I did something to 4 to get it to the 8. Not that they're showing you over here. They're setting 4p equal to 8 to solve for p. We use p to help us find our focus and help us find our directrix so that we can graph the parabola. So you're going to just set that up. It's just a real simple one-step equation. We're going to divide by 4 on both sides. And so p is going to come out to be 2. Now that's going to tell us a couple of things. Because it's positive, that means that since we're dealing with a y squared graph, the y squared graphs would either open to the left or to the right. Since it's positive, it's going to open to the right. If your p was negative at first, then it would switch and it would open up to the left because you would be going to the left to find that point. So far what we know is that our vertex is 0, 0, and we know that our p would be at 2. We use p to help us find our focus point and to help us find our directrix. The focus point, P, of 2 is just going to come down here, and we're going to write it as a coordinate, 2, 0. Because it's going to be on the x-axis. When your graph starts with y squared, that x-axis is acting like the line of symmetry, so that point's going to be on the x-axis. The directrix is that same number 2, but you just switch its sign. So it flips over to the negative 2. Another thing that you could maybe add here is your directrix here, and we saw this on the previous page, was that x was going to be equal to negative p. So we're just switching the sign there. Since it was positive 2, now it becomes negative 2. Okay, we should be able to graph these. So like I said, my vertex was at 0, 0, so my center here is just at the origin. I have my focus point at 2, 0. So that's right here. I'll just put an F by that. And then to do the directrix, it's a line through that point, x equals negative 2. I usually draw it in with a dashed line. So I'm going to go to negative 2, and I'm going to draw this dashed line like this. But I hope you can kind of see the space from the vertex to the focus and to the directrix is the same amount. It's 2 in both directions. Because of that, the distance between the directrix line and the focus is always just going to be double of whatever your p is. So in this case, it's 4. Since our p was 2, double of that would be 4. That means using that number 4, we can go from our focus up and down 4 to get another couple of points that are on my parabola. And then we can actually start to see where this is going to go. So from my focus, using the fact that p was 2, and so double that should be the distance from the directrix line that I have, and my focus is 4. From my focus point, I'm going to go up and down 4. Okay, then I'm going to draw in my parabola. So from the vertex, I'm going to connect to those points that I drew up and like above and below the focus point. Okay, now there's one last thing that they might want you to just be able to observe on the parabola. Okay, and that's this piece right here. It kind of has a weird, funny name. It's called the latus rectum. I don't know why they called it that, okay? Math people have to have their jokes too, I guess. But so this is just if I was connecting those points on the parabola. So like another almost dotted line on the inside there. Kind of, I just drew it in blue. It's not technically part of the parabola, just like the directrix is not really part of the parabola. It's just on the other side. But it does kind of just show that connection between those points that we use there. So if you see someone talking about that or wanting you to graph that in, they're just wanting you to connect those 2 points that you drew. Okay? So not as much to graph for these ones. I think the hardest part is getting used to where you get all these numbers from and keeping them straight, keeping the relationship straight between, do we go up and down? Do we go left and right? Like, what directions are we supposed to do here? So as we do more, you'll probably get more comfortable with understanding how they're all kind of connected to each other. So let's do another one here. So the first one we did was y squared equals 8x. This one now is starting with an x squared, so it's giving you another idea of a parabola. But again, x squared starts out as 4py. So they both kind of have this general form. It's just your letters changing depending on what you start with. So what should I set the 4p equal to? The 12. Okay, because the 4p and the 12 are going to go together. The y's would go together, so I need to set these other pieces together. So what would p be? 3. Okay, so this is going to help me with a couple of things. First, my vertex is still going to be at 0, 0. Okay, so I'm not changing that. So I'm just going to go ahead and write out my vertex is still at 0, 0. The fact that p is 3 is going to help me know my directrix and know my focus. Now this time, because it starts with x squared, that means you're thinking more so on like the y-axis side of things, because the y-axis is going to act like your line of symmetry. So your directrix is going to be the 3, but opposite. So we change its sign. So it's going to be y equals -3. And then the focus is also going to be that 3. But like I said, it's now on the y-axis. So the last one was on the x-axis, so we wrote that point as 2, 0 for my focus. This time it's 3, and the 0 has to come first. So it's going to be 0, 3 this time instead. This number here also can help us do that latus rectum piece. And so to do that, we just have to double it, which would be 6. So that's going to help me know some points to graph for my parabola. So remember, to graph it here, we're going to start by putting 0, 0. That's my vertex right now. My focus is at 0, 3, so I'm just going to go up 3 on the y-axis and draw a point. My directrix then would be at -3 on the y-axis, so it would be a dotted line going through -3. And then that 6 that I found by doubling the 3, I don't really care about sign for this. I'm just doubling that number 3 is my 6. That's going to tell me from my focus point, I go left and right 6 to get me other points that would be on my parabola. So from my focus, which was up here at 0, 3, I'm going to go left 6 and right 6. And then we should be able to connect our parabola. And then if you want to, you can draw in that latus rectum line as well. Questions on that example? Okay. So the next page, we're going to kind of go away from the graph a little bit. Now they're going to give us some information about a parabola, and they want us to write the equation. Sometimes they'll give you the graph, sometimes they won't. Or you could even think about like putting these things on the graph if it helps you think about how to write the equation. So what they're giving me on this first one is that my focus is 8, 0, and that my directrix is x equals negative 8. So because both of those points have an 8 in the x-coordinate spot, and they're saying that the directrix line is through the x-axis, that tells me that my equation had to lead with the y squared. So if it was opposite and the 8 was in the y-coordinate spot, or it was saying y equals negative 8, that would tell me that it has to lead with the x squared term. I also know that my focus is positive because it's at 8, 0, so I know it's going to open up to the right. So that kind of helps me know how to write my equation, that it shouldn't have a negative in it. So what I'm going to do is think about that form that I had originally, which is this y squared equals 4px. And remember, p is what we use to help us get our focus point and our directrix. So our p is 8. So they're putting in 4p, 8. So you're just taking 4 times 8 times x, and your answer is just y squared equals 32x. If you know your focus, you know your p. And then you just plug it into your formula and you're done. Just pay attention to how they're writing the coordinates so that you know, do I start my equation with the x squared or with the y squared? Okay, so if you look at the next one, is it the same as what we just did? Are the focus points written the same way? No, Deji. Okay, because this time your p is in the y-coordinate spot. So if it's in the y-coordinate, that means you have to start with x squared. So it'd be x squared equals 4py. What's my p value? Remember, it's just the number that comes from your focus. So 16. Y, what is 4 times 16? 64. That's what you were going to say, right, Tanner? Yeah. 64y. There's your equation. Questions on that? Okay, so now let's talk about how do we handle this when it's not at the origin, when it's not at 0, 0. Same idea as what we did with the ellipses and the hyperbolas. You can think about the parent function, and then you can just move everything accordingly. The other thing would be, as long as you can figure out what your p value is, that's going to tell you how far away from the vertex you should be moving to do your focus and to do your directrix. If you can just move the center point and then know what your p is doing, you should be able to graph it. Kind of like what we did with our hyperbolas. I just moved my center point, and then I used my a and my b to know what directions to move those points in. So these ones might be written a little bit differently just because of that movement that's happening. So this one we've got x minus 2 squared equals 4 times y plus 1. This would be coming from your parent graph of just the x squared being first. The only thing that we have to kind of think about with how it's rewritten now is where's your center? And so just like we've done on all the other examples, they come from these numbers that follow the x and the y, but you always take the opposite sign. So you're going to take positive 2 and you're going to take negative 1. So that's my new vertex. This number in front of the parentheses here, this 4, we're still going to use that to help me find my p. So remember I said this is coming from this equation. Originally, that's like the parent graph. So I still need to just focus on this 4p section. The y is changing a little bit because of the y plus 1. So I'm going to set 4p just equal to this 4. And that's what they're doing right there. So that doesn't really change. That's the same as what we were doing on the last couple of problems. So 4p is going to be equal to 4. You divide by 4, you get p equals 1. That means that from your vertex, your focus is going to go, since it's positive, it's going to go above the vertex by 1, and your directrix would go 1 below. Now they are showing you like where those points would actually be when I go to graph, I'm not maybe going to write out all these coordinates for these points. I'm just going to do the vertex and then actually start to do this. So my vertex is at 2, -1. So I'm going to graph that point first. Because it leads with x squared, that means you're going to be opening up or down. Since it's positive p, you're going to open up. So my focus is going to be just one above this. So it's going to be on the x-axis here at 2. That's my focus point. And my directrix would be one below the vertex. So it'd be right here. Okay, remember my p-value is used to help me find my lattice rectum points. So I double it. So 1 doubled is 2. So that's what they're showing down here. Directrix is 2. So from my focus point, I'm going to go left and right 2. And then we just draw it in. And then you can connect those if you'd like. So really not different from what we were just doing. It's just you have to think about the center is moving, and then you kind of handle everything else the same way. All right, so let's do the next one here. All right, for this equation, are we starting with x squared or y squared? What comes before the equal sign? The y squared. So parent function would look like this. Y squared equals 4px. What is my new center? And make sure you grab the numbers in the right order. Careful. There you go. -2, -3. We switched those signs, but we do need to make sure we put that 2 first. It is written backwards up there where the x comes second. We saw that happen on hyperbolas too. So just really watch for that. Okay, what are we going to set the 4p equal to? It's the number in front of the parentheses after the equal sign. So 8, but if you solve it, you get 2. So p is 2. This tells me from my center point, because the y squared comes first, it's going to go left or right. So the directrix is going to go left 2, and the focus is going to go right 2, because this is going to open up to the right since it's positive. So I'm going to graph my center at -2, -3. I'm going to go right 2 for my focus. And then I'm going to go left 2 and draw my directrix in. Okay, what do I do to my p-value to get other points on my parabola? You double it. So for like the lattice rectum part, you're going to double this. And that's going to be 4. So from your focus, you're going to go up and down 4. And there you go. We doing okay so far, everybody? Okay. We've got just a couple examples left. So we're just going to finish it here. You won't have a ton of work time here today, but I have tomorrow dedicated to parabolas as well. So you'll have tomorrow to work. But let's go ahead and finish. We've got just a couple things left. This next one is just taking a parabola and applying it to a situation here. So an engineer is designing a flashlight that uses a parabolic reflecting mirror and a light source. The casting has a diameter of 6 inches and a depth of 4 inches. What is the equation of the parabola used to shape the mirror? And then at what point should the light source be placed relative to the mirror's vertex? So they're kind of showing you, like over here on the right side, what this could possibly be looking like. And then they're showing you on the graph what this would look like. So if we were graphing the parabola that they have described here, kind of what that means. We're assuming that the center is at the origin, 0, 0. Since my diameter of like the opening is 6, that would mean from the center on each side, your widest point would be 3 and 3. And then the height is 4. So from the tallest point down is 4. So that's where they're getting all that information from. Since it's opening up like this, that tells me that my equation is going to start with my x squared. Because when it opens up or opens down, it starts with x squared. So that's where they're getting this equation from. We use the 0.34 to help us find our p. So we're just going to plug this into our equation. So we're going to put a 3 in for the x squared. So it's going to be 3 squared equals 4p, and 4 goes in for the y. So this is going to end up saying 9 equals 16p. And so my p is going to be a fraction here. It's going to be 9 over 16. Then to find the equation, for step 2, they want me to replace p, so what we just found, into my original equation. So we're going back up to this equation here. So we're going to take 4 times 9 over 16. Y, because this is going to give me just my general equation of the parabola. Now, 4 times 9 over 16, it's not going to just go away. It's not going to just be a plain whole number anymore, but it will simplify a little bit. In fact, I could even simplify right here. 4 can go into 16 4 times. So this equation is going to say x squared equals 9 over 4y. But that 9/16 that we found for our p, that would be used for my focus. And so that's where they're getting this point from. That's how far the light source should be away from the vertex, which is where they're saying the mirror would be. And that would make this flashlight work the best, is what they're saying. Oh, yeah, go ahead. All right, the last thing I have on the last page is just how you can identify conics without completing the square. So we've talked about 3 different types of conic sections in this chapter. And in a previous chapter, we talked about circles. So there were 4 conic sections total. There's the circle, there's the ellipse, there's a hyperbola, and then today we talked about the parabola, okay? If you are given an equation, like we've seen the last couple of days, especially more so in like the hyperbola and ellipse sections, some of those equations can look a lot alike because they all have x squareds and y squareds and x's and y's, so it can be kind of hard to differentiate. If the form is starting out like this, it's like your general form. So you have all these like little pieces that they're giving you. If the a and the c, so the numbers in front of your x squared and your y squared, if they're equal to each other, that means that you're dealing with a circle. So if they both were to say like 5x squared and 5y squared, those 5's matching tells me that it's a circle. Okay, so down below here, there's some examples. Which one of those seems to be the case? Which ones from the bottom 3 examples is doing what I just said a circle does? That the number in front of the x squared and the number in front of the y squared is the same. The first one. So this first one is an example of a circle. Okay. An ellipse is A and C are not equal to each other, and they're both the same sign. Usually it's addition. So which one has the number in front of A or in front of x squared and y squared, not the same number anymore, but they're at least the same sign? Is it the second one or the third one that seems to be doing that? The second one. So the second one would be an example of an ellipse. So then the last one there, let's see if it follows our rule for the hyperbola. The rule for the hyperbola, again, is that the a and the c are not equal, which they're not. I have a 4 and I have a -1, and they're also opposite signs, which is true. The 4 is positive, the -1 is negative. So this would be an example of a hyperbola. So without graphing, without completing the square, without rearranging the equations at all, I should be able to use those rules to let me know what exactly I would be graphing if I had to. All right, that is it for our notes here. So I'm going to get you guys your homework. Stop this.